Hi everyone, thank you for joining us again today for the second workshop in the Wormhole Hackathon.
Hello everyone joining. I'm Tadej and this is Mitja. We're from a company called Kalmia. We're a Web3 development studio, and today we're going to be talking about one of our clients, which is Carbify, which came to us with the goal of changing their existing project, which is Carbify, into a cross-chain project. So how we envisioned or how I envisioned this session going is first, I'm going to go through the whole process of us understanding how Carbify works currently, how their goals are, their wishes, how we change that, their architecture to integrate it now into a cross-chain protocol, just from the more architectural standpoint, what kind of compromises we had to do, what kind of discussion we had to have. And then I'll let Mitja take over a bit more practical part of actually implementing and showing you how we implemented some really cool stuff that we did for Carbify. And then we'll go even a bit deeper into how to debug, or if there's some problems, how to sort over. Okay, so introduction is done. Let's hop right into. First, just to tell you what Carbify actually is. This is an existing product which is for certified carbon offset. Now, in practice, this means that they are selling NFTs, which are trees, and these are real world assets. And each NFT tree you buy, it's linked to an actual tree or multiple trees that are planted and grown in different parts in the world, from Vietnam to Africa, etc. And since these are real trees, those trees take CO2 from the air, and based on the trees and how old they are, how tall they are, they have a specific rate of how much CO2 they consume. And based on that, a CO2 token is generated for the users. Now, the user, the one that bought the NFT tree, is now getting a CO2 token. Based on that, has two options. Either he burns this ACO2 and gets an official carbon offset certificate for the amount of carbon offset he did, or he can sell this ACO2 to others that want to do the carbon offset. These are mainly companies or some individuals, because a lot of the companies have, by law or by regulation, they need to offset an X amount of their carbon footprint. And this is one way of how they can do that, and then how they can prove that. And of course, with users buying NFT trees, they produce that much planting of the trees and a self-fulfilling cycle afterwards. So this is the basic workings of how Carbify works. And from the technical standpoint, or from the on-chain standpoint, this means that we have multiple NFT tree contracts or ERC-721 collections, each for, when they go and they plant tons of trees at once, they create a whole collection, then you can buy parts of those planted trees. And then we have an ACO2 smart contract, which also holds the main logic. This contract is connected to the NFT tree collection in a way that each time a new collection is created, it's also added to this contract with their specific emission rates. And the user can then claim, and so he buys the NFT tree, he has it in his wallet, automatically the ACO2 starts producing, he can claim it at any point, and then he can burn it and create a certificate from it, which is also an ERC 721. So let's say the architecture on-chain currently is pretty straightforward. And one thing I want to note here is also that the user can sell his NFT tree. That's his tree, and at that point, he stops claiming, so the ACO2 that's being produced is now being associated with another user. So each time an NFT tree is transferred to another owner, the claiming of ACO2 happens automatically. So it's triggered so that the current owner gets all the ACO2 that was produced while he was owner of the tree, and afterwards the producing of ACO2 goes to the new owner. So Carbify came to us. This project was already done to this degree, but they now wanted to expand into cross-chain. They had, so still have, very specific goals for this. First is currently this protocol is deployed on Polygon, but they want to expand into new ecosystem. This is because still the, let's say, the Web3 world is a bit limited with the amount of customers, and they want to go where new potential customers are. And it's simple for users, whatever chain they're using, that they can still buy the NFT trees. So their main goal is expanding the, let's say, the buying of NFT trees into multiple ecosystems. And but this can be a bit problematic from the standpoint of complexity, if this would be like multiple copies of the same protocol near every chain. So they wanted to do it cross-chain, where then the ACO2 that's being produced is being produced on a single chain and the certificates are being there. So this way they can expand into different chains and different ecosystem, while the logic and it's the simplicity still comes from one single chain at the end. So with those two goals, the third goal was that adding new chains should be very simple to the architecture to be built, and that the user experience still, stays in a reasonable limit, so it doesn't become too complex or too slow just because you're going cross-chain. So speed and price matters here. With this in mind, we set up an architecture, which is a hub and branch system, or master slave, however you want to name it, where we have one central logic contract, which is deployed in this case on Moonbeam. And we have now multiple NFT tree contracts or collections that can be deployed on different chains. The reason why the hub contract is on Moonbeam is, so why this decision was made, is because first, it's a layer 1 blockchain and has fast finality. So any kind of wormhole calls or messages will have fast finality. The second is that besides wormhole, Moonbeam is on Polkadot. It also supports native cross-chain messaging of the Polkadot protocol. So if they want to expand into Polkadot chains, it becomes pretty easy from that. So these are and then the ACO2 is produced on base chain. And the main reason for that is basically more of a business decision than a technical one. I guess it's the hot chain right now, and they decided with base chain, or the cheapest, the base chain as where the ACO2 is being produced. So with this architecture, now you can see there's multiple wormhole calls that are being made based on what kind of transactions are happening. Now, there are a few considerations from the get-go. First is, if you do a cross-chain call and you use wormhole for that, which we are obviously doing, you need to pay the fee for that message to come from one chain to the other. So first is, who is paying that fee? One option could be that the smart contract could come loaded with some fee token, and anytime a user would do a transaction from the smart contract, that fee would be taken. In this case, the company, so Carbify, would be sponsoring the fees. The second option is that the user, when they do a transaction, also add a bit more, in this case, Matic, to the transaction itself to cover the wormhole fee. In this case, this is decision you need to do also on how your revenue is, how your business model is, how your users are. In this case, we collaborated with Carbify that users will be paying for those fees. The second is what happens when an NFT tree is transferred. So as I mentioned before, currently when an NFT tree is transferred, a claim is automatically triggered so that the current user gets all the ACO2 he owns. Now with the cross-chain, if I go a bit back, with the cross-chain tree is being transferred, there's a wormhole call that needs to be made to the hub contract. And from the hub contract, another call to ACO2 for it to be distributed to the user. So this means that when you're transferring an NFT, you need to add a bit of the value, so a bit of Matic or whichever to cover those hops. That's why we were considering here two different scenarios. One is either adding the value when doing an NFT transfer. The second one's to do a state collector contract on each of the chain, or probably inside the NFT collection, which would track the states, and only when the user claims the ACO2, then the calls would be made and the calculations, which makes the architecture a bit more complex. Now, we opted in for user paying the fee on each NFT transfer. This is because currently Carbify, already knows their customers. They know that the NFT does not trade that much. Once a user buys the tree, they usually keep it for quite a while and they produce the ACO2. The second is that they have their own custom marketplace already. Because if you do a transfer of an NFT and that needs, additional value, so some additional Matic with it, like standard marketplaces don't support that. So like OpenSea does not support it by default. So because they have a custom marketplace, this is not a barrier of any kind. The second is more technical changes or things you need to think about. So if you look back, the main logic that was before inside the ACO2 is now separated and it's all inside the hub contract. This is a whole new contract that was not there before, and ACO2 is now a clean token. Second is you have things like two wormhole messages in a single transaction. So basically with the NFT tree transfer on Polygon, you need to do a cross-chain transfer to the hub contract, and from the hub contract to the base ACO2 to mint it. So when you do that, you need to figure out what the fees are for the first hop and for the second, as well as what are the gas prices and limits. This means you need to do 2 RPC calls on 2 different chains to calculate exactly what the fees are going to be. Then there's limitations of the amount of ACO2 tokens that can be claimed at the same time, or I should better say how many NFT tree collections can you claim from at the same time, since there are still multiple calls that need to be made. So there's some limitations that you need to consider and calculate beforehand. And because there are quite a lot of cross-chain calls being done, especially with 2 hops, you have to think about things. What if one hop fails? So one goes through, the second fails, or in what kind of state it is. Or if you're doing multiple calls, in what order are they coming so that one is not processed before the other? I'll leave you with details of this more into Mitja later on. And all of these now produces, with all this in mind, here is a user flow, which Mitja will also showcase later how it's done in the contracts. But so that you have a really good overview, if a user does a NFT transfer, he will first, with the NFT transfer trigger, he'll add some winding fee and base fee. Those will be 2 RPC calls that he'll have to create. He'll do this on the Polygon chain, which will do a wormhole call to the hub contract. It will give the hub contract the information about which NFT was transferred and to whom, which is the new owner. The hub contract will calculate when was the last time the ACO2 was claimed, and now what is the emission between that and current time, and trigger a call to ACO2 on base with the amount of ACO2 to mint. And this will then mint the ACO2 and send it to the user. So this is basically how like our thought process was with going through the architecture to see what the options are, to see what limitations, so that you have now a bit of a feeling how the basis was, and to what kind of architecture we now came with the help of wormhole cross-chain messaging. And I'll leave it to Mitja, and he'll tell you a bit more about how this was now practically implemented.
Hey guys, let me just share the screen and we can start on the technical part. Okay, so here. So I've split my part of the presentation into 3 sections. Firstly, I'm going to show you 2 cases. So the basic case, it would, as I called it, it would be the NFT mint that only has one cross-chain call. Then I'm going to show to you advanced case that is an NFT transfer call with two hops or cross-chain calls. And then I'm going to talk a bit about debugging and considerations, at least about the problems we faced during the integration. So firstly, for the purpose of this presentation, I prepared a demo repository, which is like a very simplified version of the Carbify project. But the key components that are relevant for the cross-chain integration are left in. Otherwise, all the unnecessary logic that is not relevant is thrown out. So the prerequisites for the cross-chain implementation are obviously the source and destination contract. Then you're going to need the two interfaces, the wormhole relayer and wormhole receiver. And we'll be using the wormhole automatic relayers. This way, we don't need any front-end or back-end logic with regards the actual cross-chain message propagation. It's all done by the wormhole service. So yeah, in our case, as they already said, we'll be using 3 contracts: the NFT tree, the Carbify hub, and ACO2 token. And the only difference that I made for the demo is I won't be using not Mumba, but Amoy. But instead of Amoy, which is a Polygon testnet, I'll be using the Cello testnet. And the reason for that is because the Amoy testnet, it doesn't have an automatic relayer deployed yet. So because the migration was not long ago, so yeah. But otherwise, it's also a Cello testnet. It's also a EVM, and it basically doesn't matter from the technical view. So yeah, now let's go through the NFT mint. So our goal here is to basically on every NFT tree mint, we want to pass the owner of the newly minted address to the hub on the Moonbeam chain. So I'll quickly just go through the steps you need to take, and then I'll show you in the code so you can better understand. So on the source contract, you need to import the wormhole relayer, then specify the wormhole relayer and hub address. The addresses for automatic wormhole relayers can be found in the wormhole docs. So yeah, then you need to specify the destination chain gas limit for the destination transaction and the receiver value. The receiver value represents the amount of gas token that is going to be airdropped in the destination contract in the destination transaction, if it sounds reasonable. Okay, and then you need to encode data into payload, whatever you want to send, and execute the transaction on the automatic relayer. In the destination contract, you need to import wormhole relayer and extend wormhole receiver, and again specify the wormhole relayer address and whitelist the all NFT tree contracts that you want to allow to be sending messages onto the hub contract. And then the most relevant part is to implement the receive wormhole messages function where the magic happens. So yeah, before I show you the code, there are a couple of crucial checks you want to implement in the receive function. because the receive function is a public function, you want to restrict who actually can perform action on it and so on. So yeah, what you should be checking almost every time, that the only allowed address, that so the message sender in Solidity should always be the wormhole relayer. If required, you need to verify source chain and source contract address. This is the address that initiated the cross-chain call. In our case, this would be NFT tree address. And then you can decode the payload and determine if the decoded data is actually valid. So now I'm going to jump out of the presentation and going to show you here in Solidity. So yeah, this is my demo repository. I have 3 files: the NFT tree contract, hub contract, and ACO2 token. And yeah, I'll go firstly through the NFT tree. So as I said before, you need to import the wormhole relayer. Then you specify the wormhole relayer address and hub. Then you initialize it in the constructor. And then we are already here in the mint. So in the mint function. So firstly, the important thing is that your function needs to be the function that is going to call the cross-chain call. It needs to be payable, because you need to, as Tadej said, we are going with the approach that user pays for the cross-chain transactions. That means that you need to pay some extra gas token when you're calling, in this case, mint function. So yeah, here we are just minting tokens and basically saving the newly minted tokens into the IDs array. And then here is the important part. You need to encode whatever you want to send to the other chain into the payload. So here in our case, we have 4 parameters. You could have 10 or 20 parameters. It doesn't really matter. The important thing is only that you decode it then on the destination chain in the same way you encoded it on the source chain. So you basically on the destination chain, you know what to expect and which types you'll get. So yeah, here we have the first parameter stands for, one is mint and the second is for transfer. Then we have the user that is just received the newly minted NFTs, block timestamp, and then we have the IDs array. That's it. Then here.
Can I just interrupt you a second?
Yeah, sure.
Are you able to zoom in your?
Oh yeah, sure. Just a second. Isn't it? Wait, I to be honest, I'm not sure.
In view in the.
Okay.
Oh, there
I
we go.
found it. Okay.
Nice. Thank you very much.
Okay. So yeah, now we went through the payload, and then you need to specify the target chain, the receiver value, and gas limit. The important thing here in the target chain is these IDs are not EVM IDs. These are the actual internal IDs of wormholes IDs, because they also support non-EVM chains, and that way they need to have their internal IDs. And 16 stands for Moonbeam. Also, these IDs can be found in the docs, so navigate there if you need them. The receiver value for the mint function can be left to 0, because, as I said before, we don't need any airdrop in the destination transaction. For this case, for the NFT transfer, we are gonna need it, but let me talk about that later. And here we have a gas limit. The gas limit can be basically whatever you want. The important thing is that you set the sufficient number that you know that you're not gonna surpass in the destination transaction. If you set gas like really high, or there is a lot of gas left over that was not used, you actually get a refund of the overpaid gas. And I'm gonna show you later where you specify the refund address. So yeah, then you need to quote the delivery price. This is basically the cost of the cross-chain. This is basically the wormhole fee. And you call this function and supply target chain, receiver value, and gas limit, and you get the exact cost. And then you can actually initiate the cross-chain call by calling send payload to EVM with cost, and then these first parameters I think are pretty clear. And here is then where you can then set on which chain you want to receive the refund, in case there is any, and the address you want to be sending the refund, receiving. So that's basically all from the source contract for the mint. Then I'll navigate to the hub contract. So hub contract is our destination contract. It's where we want to be receiving the cross-chain message. We import the relayer and the receiver. Then we extend the receiver. Okay, so here I have wormhole relayer address, ACO2 token, which are going to be needing for the NFT transfer, for the let's say for the advanced case. And then I have two mappings. The first mapping is basically for each NFT tree that you want to be allowing to send cross-chain messages to hub. You need, because you're with the owner permission, you need to whitelist it. And then we have an owner's mapping, which will basically store the current owner of each NFTs of each collection. If that sounds okay, if it sounds reasonable to you. Yeah, okay. So yeah, here we have the wormhole receive event that we're going to be emitting. And again, we initialize the wormhole relayer. And then here's the important part. The receive wormhole messages, it's already defined in the relayer interface. So you're going to be overriding it. And the data you're receiving in the destination contract is the payload, additional VAS, source address, source chain, a delivery hash. And for our integration, the only relevant data were payload, source address, and source chain. So yeah, here now we have the crucial checks that we need to, that I've spoken already before. So you need to be checking that the sender is actually the wormhole relayer. Then you want to be checking that the source address and actually that NFT tree that triggered that cross-chain call was actually whitelisted, so that it doesn't come to some unauthorized access. So here I have a little helper function. We need this function from wormhole format because I said already before that wormhole supports also non-EVM chains, and some chains have longer addresses. And this is why you need to basically cast the source address from bytes 32 to native address type solidity. And then if nothing is reverted, that means that crucial checks are okay. Then you can decode the data. You basically, these are then what you encoded here. You then decode it in the source contract, you then decode it in the destination contract. And then here I gotta check, because only available modes for us are, one is stands for mint and two stands for NFT transfer. And then this part I'm gonna skip because it's only relevant for the NFT transfer. And then here you save the new owners that from the source chain of the newly minted NFTs. And then here in case of mode one, so in case of mint, we do nothing extra. And in the end, we only emit an event. And this, I really recommend you always put the emit event in the end of your receive function. It's really gonna help you debug a lot, because otherwise in some cases, it's a bit of black box to debug on the destination chain. And now I prepared also the NFT mint and NFT transfer script. And firstly, I'm going to run the NFT mint and show you on a real example how it works, or at least it should be working. So yeah, NFT mint, this is my already deployed collection of NFT tree on the Cello testnet. So here I initialized the wormhole relayer on Cello. I only needed to get a quote. So basically to get the wormhole fee, how much it costs to propagate the cross-chain message from Cello to Moonbeam. Then I specify the quantity I want to be minting. And these values are set the same as they are hard-coded in the NFT tree. And then I call mint with passing value, so the wormhole fee. Now let me run npx hard hat run network Cello testnet script NFT mint. So if everything goes well now, it should work. Let's wait a second. Okay, so mint successful. Let's check the transaction. Okay, so here's the transaction. As you can see, we also sent some value. This is the amount used for wormhole fee. And from here, here you can check which ID was actually minted. And this is so transfer event from 0 to some address. And the token ID is 4. So you know which token ID we should be watching. And I can now show you in the wormhole scan how it looks like from their perspective. So yeah, the transaction is already completed. You can see the transaction was from the Alpha Hores, that is Cello testnet, to Moonbase Alpha, and everything is okay. And also here I have my hub contract, and this is owner's mapping. And this is already, I tested before, this is already 14 stands for Cello. This is the NFT tree address, and I can check if the owner was successfully transferred. And you can see that my address is set. This means that the actual cross-chain message was delivered. If I check for token ID 5, I get 0 address because token ID 5 wasn't minted yet. Okay, so this is it what regards the basic case. Now I'm gonna quickly show through back to the presentation and through the advanced case. Yeah, this case is a bit more tricky because it has 2 cross-chain calls. So our goal here is to actually on every NFT transfer, we want to pass the new owner to the hub. And then when the new owner is stored, we want to claim reward for the previous owner. For the time that he was holding the NFT, the appropriate amount of ACO2 tokens should be basically minted to the previous owner. So I'm gonna just walk you through the steps that are not the same as they are in the NFT mint, because most of the logic is the same. So in the source contract, the NFT tree, you need to, before doing basically everything else, you need to quote the second call cost and use it as a receiver value in the first call. Now, if I explain this a bit, this just means that you need to quote get the cost, how much it would cost to for the second cross-chain call, so from hub to ACO2, and pass that extra amount into the first cross-chain call. So basically, you'll be top-upping a bit of gas to the hub contract, so that way hub contract will have funds to actually perform the second cross-chain call. In the destination contract, that would be the hub. The destination contract of the first cross-chain call. that would be the hub. In the receive wormhole message, you just need to, after all logic, so after saving the new owner, you need to add another cross-chain call from Moonbeam to base with payload containing instructions for ACO2 mint. And then the hub contract in the first cross-chain call, the hub contract is the destination contract, and in the second call is actually the source contract, and the destination for the second cross-chain call, or we could call it the final destination of this entire process, is actually the ACO2 token on the base chain, and there you only need to whitelist hub as an only authorized sender. Okay, I'm gonna jump back to my code. So here, okay, we start with NFT tree. Yeah, everything up here is the same. Yeah, firstly, what already Tadej talked about, since we need to be sending a bit of gas token, the standard transfer functions of the ERC 721 don't support overriding with adding payable. So we firstly need to disable the standard functions and add our own transfer from payable with the payable mark in the end. So here, firstly, we perform the standard transfer of the NFT. And then, as you probably noticed, we have, along the standard parameters, we have an extra parameter, a receiver value. This is actually the cost I was talking about before for the second cross-chain call, which needs to be calculated on the Moonbeam RPC separately and then just passed here, because the Cello itself, it's not aware of the cost between the Moonbeam and the base chain. So yeah, here, since you can only transfer one token at a time, we're gonna have an array of one token, and here we have the same payload. The same structured payload with set 2 for transfer. 2 is the new owner of the NFT. Again, block, timestamp, and IDs array. Here we set again the same as before. The only thing missing here is the receiver value, because we are querying it on the Moonbeam RPC. We pass the parameters and we get the actual cost for the entire process of so actually for the both cross-chain operations, cross-chain intersections, and everything here then is the same. You just initiate the send payload to EVM on the wormhole relayer. Then we have hub, which is the receiver of the first cross-chain call. So again, here everything the same as it was in the mint case. If I jump to receive wormhole message, here again you check the crucial checks, you decode the data, check if the mode is valid, and then here, before changing the owner, you save the previous owner, so you can then pass that owner, which should be receiving ACO2 tokens on the last part of this whole process, so on the base chain. And here you have, in case there is a transfer, you need to firstly set how much of ACO2 tokens every let's say user should be receiving. Here I simplified it and hard coded to 10 tokens. So every time, and the reason I did that is because Carbify logic for emissions is a bit complex, and it's really not relevant to complicate things with that. So every time, basically in the demo, every time a user performs a transfer, the previous user will get 10 ACO2 tokens airdrop. And that's basically it. And then you encode the relevant data into payload. And here, again, it's almost the same, except the target chain is set to base Apolia. And we calculate the cost and then initiate the actual second cross-chain call, which is then executed, delivered into the ACO2 token, which again imports. I'm going to keep the parts that are the same. You set the hub, and again, you have the receive. Don't forget to extend the wormhole receiver, and then you have the receive wormhole messages, and check the crucial checks, and then you just basically decode and mint the tokens, and emit an event. Don't forget that. So now I'm going to show you this, the NFT transfer on a real example. And I'm just firstly going to jump to the code of the script. So this is my already deployed tree contract. Here's because I need the second hop to be cost of the second hop to be calculated in advance. Here I have my Moonbeam provider. Here I'm defining two relayers for Moonbeam and for Cello. Here I'm quoting firstly for the second call and secondly for the first call. Why is the order firstly for second or secondly for the first? Because you actually need to pass the cost of the second hop into the receiver value, which is needed for quoting for the first cross-chain transaction. And here I'm gonna set, I think that, I'm not sure which ID. Okay, we minted the fourth token ID, so I'm gonna change it to 4, and this is the token recipient. Here is just some not relevant check. I'm really the owner of the NFT, and here I'm calling then my function transfer from payable. And so the sender address, or previous owner, new owner, token ID that I want to transfer. This is the value for the second cross-chain call, and then is the value for the whole process, what regards the wormhole fees. And now I'm gonna run transfer. Okay. Let's wait a second now. Okay, so transaction is successful. Here you can see the costs of the second hop and the cost of the entire cross-chain operation. The total cost is lower because it's not in the same currency, so not to confuse you. So now let's check a bit our transaction. Here it's everything. Nothing much to say. Nothing. I mean, it's almost the same as the NFT mint. But now here, let's insert the transaction into wormhole scan. Now we can see the first hop of the first part. So the actual NFT transfer happened on Cello, and was then the new owner was propagated through wormhole to the hub address on the Moonbeam. We can check if the actual owner was changed. So this is the previous owner. The new owner is changed. And now we can check. If we click on the copy the transaction and insert it into wormhole, we should be seeing the both hops. Just a second. So okay. So here is if you insert the target transaction of the first hop into the wormhole explorer, you'll then see the whole process. Here is the first, so the NFT transfer, new owner to Moonbeam, and then you can see the second transaction, Moonbeam, instructions for mint on ACO2 on base chain. And if we actually open let's say the final transaction on Moonbeam, we can see that there were actually 10 ACO2 tokens minted on base. And that's it what regards the examples. And now I'm going to jump back to presentation. Okay. Oh, sorry. So yeah, now I'm just gonna go quickly about say something on topic of debugging and considerations. At least I'll say something about problems that we were facing. So yeah, firstly, use wormhole scan. It's really helpful. You see all the necessary data and it works really great. Then always submit an event on the destination contract. It's really gonna help you, because otherwise it can be pretty frustrating and like black box on the destination chain. So if your transactions are failing on the source chain, it's very probable that you are sending the wrong wormhole fee in the value. So check that. If the transactions are failing in the destination, on the destination chain, then there are several possible problems. So it might be the gas limit, that gas limit is reached. It might be that it is the cross-chain call is initiated from unauthorized address. And maybe you even have a syntax error in the destination contract. And then what regards the consideration, we were facing this problem and just basically resolved it with a bit of help of the wormhole team. In section order or destination chain can mix up due to network congestion and concurrency. This is basically if you have a lot of transaction, let's say almost simultaneously triggered on source chain, wormhole doesn't grant that the order of the destination transactions will be exactly the same that were triggered on the source chain. This means that if you have some sensitive data and some, let's say, amounts and rewards and it's money involved, you really should have some internal, let's say, nonsense that you grant yourself that the order was really the transactions really arrived in the right order and prevent any, let's say, lose of funds and stuff like that. Okay, so now I'm gonna pass the word to I'll pass the word to Tadej, because I'm finished with my technical part.
Yeah, so this was mainly it. Hopefully we didn't go too deep or too technical. I'm gonna share now the URL for the code that Mitja presented. You can also scan the QR code to see the example project on GitHub. And you can also see my contact information from my Twitter to company page and email if you need any kind of help from our side. Also, we would open now things for questions. I already received one, so there was a bit of confusion. What is the whitelist part on the destination smart contract? This is mainly, okay, I'll just share a bit from my side as well, so you can still scan the QR code and see the information. So basically on the hub contract, we want to limit who can actually call the receive wormhole messages function. So that we limit it that only the smart contracts that we deployed our NFT collections on transfer do the calls. Otherwise, because that function is public, so anyone could call it. If we don't limit it, and that's the whitelist addresses part, if we don't limit that, anyone could hack or call that function with whatever parameters they wanted. So this is how we limit it to only smart contracts that we deploy on the different chains. And this is not in a way that when you implement this, you limit that to your contracts that you are deploying. It's not a thing that it's from a wormhole and you need to find it in some kind of documentation. It's our own limits to say which smart contracts can. I think there was one question also for fractional ownership. Since these are NFT trees, they're not by itself on such, let's say, high amount of value. So it does not make sense to only buy a quarter of a tree, which they're not that expensive. So you can there's no reason really to support fractional ownership, but you can buy smaller and bigger plots of trees. So for the whitelist contract, where to submit it, so we deploy the Hop smart contract on, let's say, Moonbeam, and we deploy NFT trees on Polygon. When we deploy the NFT trees, we know the contract address, and as we have ownership, we can set that contract address on the hub so that only the NFT tree can send the message to the hub and the hub to receive it. So this is not automatically approved. You need to add that logic into your smart contracts.
So basically, every time you deploy a new tree contract, you need to basically link them together by whitelisting
Correct.
the NFT tree address
Yeah.
onto the hub contract.
Since you're basically talking about completely separate chains, so let's say Moonbeam and Polygon, they're not aware of each other at all. So that's why you need to specifically set and link them together. So for the whitelisting, it's something you can add the logic yourself.
Yeah, it's like the only owner function to just, in some mapping, flip one Boolean value to true.
Yeah, you can also see this in the Mitja's example. If you're struggling a bit, please check just the simplest example of one hop. That will be the easiest. And you can see there in the smart contract, it's a mapping with whitelisted addresses, and basically the contract that you deployed on Polygon, for example, is then that contract address is set as whitelisted on Moonbeam, and that's just a separate smart contract call on Moonbeam to set it. That can only be done by the owner of the contract. Yeah, Ivan, thank you. We believe as well that it's quite an interesting project, and a lot of companies by regulation, even at the moment, need to do their carbon offsetting. So I think it's a really good use case for blockchain, and it's basically a kind of investment also to buy a tree. So it kind of brings together an investment basically, plus you're still doing something good for the nature. So it's a pretty interesting project. Thank you.
I think there might be, I think you might have answered all of the questions. There's this one at the top of the questions tab. I'm not sure if you've covered that. Can we show and track the status of the cross-chain calls to users?
The question, I can't really find it.
I can put it on the screen. You should see it on the.
Yeah. Can we show and track status of cross-chain calls to users in our website? Yeah, I mean, we can gather that information from Wormhole exec specifically, right, Mitja?
Yeah, I'm not sure, but they probably have some API to fetch the data of the specific cross-chain transaction, but otherwise you could have your own indexer and parse events that were submitted on the destination and link them together. But I'm almost sure that they have like their own API that is like very simple. Since they're already displaying all the data on their wormhole scan, they probably have some API.
That would make sense, wouldn't it? We can look into this and get back to you, Arthur, if you still have more questions, put them in the Discord. So we've passed our time now. So thank you very much, guys, for coming in and giving that workshop. That's going to be really useful for people to rewatch, especially the demo going through with such an interesting use case as well. So thank you very, very much for that. Just one note on the hackathon as a whole. I've started contacting teams and sending out emails just to check in how you're doing. So if you get an email from me, please do reply to it. Let me know how you're doing and what you're planning on building, because I'd really love to know and keep in touch with you throughout the next few weeks. But otherwise, that is our workshop over. There are no more questions and no one is typing. So I think we can assume that everyone has understood and is happy with the session today. So thank you very much again for coming in, guys. And thank you everyone for joining us again today. I hope you enjoy the rest of the hackathon as you're building. As I say, please get in contact if you have any questions. Keep asking your questions in the Wormhole channel on the Discord. Yep, lots of thank yous in the chat. Okay, awesome. We'll leave it there for today. The recording of this session will be up tomorrow, so you can rewatch parts of the demo if they're useful for you. I'll also post the link to the GitHub in the Discord channel in case you missed it, so that you can go back and have a look at that as well and fork it. Okay, thank you very much, everyone, and enjoy the rest of your day.
Thank you all.
Thank you for having us. Bye.
Cheers.
Bye.